Hi, I am Steve Frey, and I am presenting a fully integrated groundwater surface water forecasting in two contrasting hydrostratigraphic settings within Southern Ontario. I'd like to acknowledge my co-authors, as well as our collaborators at Quinte Conservation, Long Point Region Conservation Authority, the MECP, the Geological Survey of Canada, and the Ontario Geological Survey. The work I am presenting here today stems from a project that we had done collaboratively, developing a fully integrated groundwater surface water model for all of Southern Ontario during the 2014 to 2019 Southern Ontario Groundwater Project. The objective of the project was to calibrate two watershed scale models that were derived from the Southern Ontario regional model under transient groundwater level simulation, as well as for transient flow simulation. We wanted to deploy the two watershed scale models in a proof of concept groundwater forecasting application, producing 7-day and 32-day forecast intervals. And we want to demonstrate a web portal capable of disseminating groundwater level forecasts to stakeholders. The map we are looking at here depicts all of the watershed regions that are encompassed within the Southern Ontario regional model. The two circles highlight the Quinte region watershed and the Long Point region watersheds that are of focus in this study. The Long Point region watershed encompasses approximately 4,000 square kilometers, while the Quinte region watershed encompasses about 7,000 square kilometers, as represented in the model. The two watershed models that we're looking at were carved out from the regional model database that we constructed previously. Both of the models in this project carry the hydrostratigraphy that was developed for the regional scale model, including all the subsurface layering, and the initialization for each of the watershed models carries the same permeability maps and spatial distribution that we had in the regional model database. Here we're looking at the assembly of the hydrostratigraphy in the Quinte region model. To the northeast in the model domain, we have fractured bedrock, and then we see that the Phanerozoic hydrostratigraphy starts draping over the fractured bedrock with a dip to the southwest. Overlying the Phanerozoic and partially the Precambrian is discontinuous surficial deposits. Here we're looking at the assembly of the hydrostratigraphy in the Long Point region model, with the stack of Phanerozoic material underlain by the surficial deposits and then the soils layer. The hydrostratigraphy in the Long Point region model is considerably easier to manage than the hydrostratigraphy in the Quinte region model, and was much easier from a model calibration standpoint. Here we're looking at the ability of the Quinte region model to reproduce daily surface water flow rates across the watershed, with flows simulated at 16 hydrometric gauging stations being used to evaluate model performance. For the most part, the NSE value is 0.5 or greater, indicating good performance, and even the lowest performing station demonstrates that the model does capture the peaks and valleys associated with the transient conditions over the 2011 to 2018 model evaluation interval. Here we're looking at the distribution of PGMN wells across the Quinte region watershed model. There were 31 in total that were implemented into the model and used to evaluate the model's ability to reproduce transient groundwater levels over the 2011 to 2018 time interval. On the top right, we can look at the simulated versus observed water levels averaged over that simulation interval, and for the most part, there's less than 5 meters difference between the simulated and observed water levels, although there are a handful of wells where the model does overestimate the groundwater levels quite notably. It's important to recognize that there's no groundwater extraction implemented into any of the models we're looking at here today. And For a higher level perspective on groundwater simulation performance, the bottom right figure shows water levels in the observations plotted against water levels in the simulations relative to sea level, and we have an R squared of 0.99. Not that these types of plots really give anybody much insight on how the individual wells are performing. Here we're looking at the surface water simulation performance for the Long Point region model. The map on the top left showing the distribution of the hydrometric gauging stations across the model domain. The bar chart in the bottom left showing the NSC values for the model's ability to reproduce observed flow rates at the hydrometric gauging stations where there was a long enough data record to support evaluation from the 2011 to 2018 simulation interval. For the most part, the NSC values are approaching or above 0.5. There are a couple stations, though, that are pretty severe outliers, although it's interesting when you look at the time series for the largest outlier in the top right panel here. The trends generally match okay. It's just that we're not capturing the peaks and the low flow conditions accurately, with the model overestimating the peak flows and underestimating the base flow conditions. Whereas if you look at the figure in the bottom right, which is the time series of simulated versus observed flows at the best performing hydrometric station, the model's closer at both the reproduction of base flow and peak flow conditions. Here we're looking at the groundwater simulation performance for the Long Point model. The map in the top left depicts the location of the PGMN wells that were implemented into the model. Those wells, which had continuous monitoring data for 2011 to 2018, were used to evaluate model performance. The bar chart in the bottom left shows the difference in average observed water levels and average simulated water levels over the 2011 to 2018 time interval. For the most part, the differences are less than 3 meters. But there's one well where we see the difference is 13 meters, with the model overestimating the water levels. The transient characteristics of water levels are depicted for 4 wells in the time series plot in the top right. 3 of the 4 wells demonstrate that the model captures the magnitude and timing of interannual variability quite well, but the 4th well obviously shows that the model isn't quite as sensitive as the actual well in the real world, and we're not capturing some of the significant drawdowns that are observed in the actual observation well. And then, not that it means much, we're also showing the simulated versus observed water levels averaged over the 2011 to 2018 time interval using sea level as a datum, and we have an R squared of 0.97, but this doesn't really tell us too much about the performance of individual wells. In this slide, we're looking at the layout of the forecasting platform and web portal that's been developed to disseminate the surface water flow forecasts and the groundwater level forecasts that we're producing with the models. The location of the surface water monitoring locations are identified with the flags in the bottom left map. And then, just as an example of a 7-day forecast for surface water flows, we're showing what the forecast, the delivery looks like for surface water flow rates, with the black line showing the observed surface water flow rates up until the point where the forecast was launched, and then the red line showing the median forecast surface water flow at that location for the next 7 days, and then the green lighter band that's surrounding the median line shows the difference between the 10th and the 90th percentile. It's important to note here that we're not running a single deterministic forecast, but we're actually running 21 forecasts that allow us to evaluate some of the uncertainty in the forecast going forward based on the uncertainty in the weather forecast. So obviously, uncertainty in the weather forecast translates into uncertainty in the hydrologic forecast, and we're trying to capture that statistically here. As I had mentioned earlier on, one of the objectives is to use these updated models for the Quinte and Long Point regions to provide groundwater forecasts. So here now, we're looking at the Quinte watershed and the location of the PGMN wells depicted in the forecasting platform. So at each one of these locations, we're producing groundwater forecasts for a 7-day forward-looking window that's coincident with the timing of our surface water flow forecasts. And we're also producing now a 32-day forecast, which is a sub-seasonal forecast. We generate that once per week. So what we're demonstrating here in the chart on the bottom right is a flyout of the groundwater forecast produced for one of the PGMN wells. And similar to the surface water flow forecast, the red line is the median level forecasted for that well location, and the green bandwidth describes the difference between the 10th and 90th percentile. So again, we're using an ensemble type of approach to capture some of the uncertainty. So beyond just trying to forecast groundwater levels, we're also starting to think about how we could potentially forecast groundwater discharge. In the map we're looking at here, we're seeing groundwater discharge produced in forecast mode for the streams throughout the Quinte watershed. While this is still a work in progress, we anticipate at some point we'll be able to extend our forecasting capabilities to groundwater surface water interactions. So in the next slide, what we're looking at is the ability to potentially forecast groundwater recharge, spatially distributed across the entire watershed, and deliver these types of information with the forecasts for groundwater levels and surface water flows. So in conclusion, I'd just like to reiterate that extracting regional scale hydrostratigraphy from the regional model for use in watershed scale models, where we're looking to reproduce the transient groundwater levels in the PGMN wells, is definitely viable. Some watersheds will definitely be easier than others in terms of calibrating the watershed scale models, as we saw with Long Point being quite easy, whereas the Quinte region watershed required a little bit more effort. Definitely, if you're thinking about watersheds like Quinte, fractured Precambrian bedrock, as well as the role that the interface aquifers play, needs to be considered. We'll highlight that we have forecasting framework in place now to provide medium-term and sub-seasonal groundwater forecasts, as well as surface water forecasts. And because the hydrogeosphere fully integrated modeling approach implicitly resolves groundwater surface water interactions, we can now potentially look at forecasting groundwater discharge and groundwater recharge, although additional work will be required to fully develop that capability. So in closing, I'd like to say thank you for listening, and I'm happy to answer any questions.